Dear Reginasailing family and friends, this was maybe very theoretical, but now when we use our template, I think we will get quite close to understanding how simple it is step by step, because you're going to do it over and over again. So I have my sharpener, my eraser, my pencil, and my wonderful nautical almanac. Today we also will use the sight reduction table. So for this we will have a morning shot. We will go up in the morning and shoot the sun, and for this I have this beautiful template which looks very complicated, but it isn't, because it is step by step. It is these 5 steps. First, here we have the measured angle, and we note what we have measured the angle on the sextant. We do the corrections to get to the observed altitude. That we already did on the noon sight template. Now this is the sight reduction template for the sun. The second step is in the blue book. That's to determine the position of the sun. We do this here, and we use a little sketch here on the globe in order to decide which longitude we want to choose in order to get a full degree of local hour angle. I'll come to that very soon. Step 3 is to find and calculate the altitude HC and the azimuth. We use the sight reduction table for that, and we do this here with a little correction table that does also belong to this purple step 3. As step 4 in green, we compare the 2 altitudes. We compare the HC, which we have found in this step, with our own HO, which we have found in the first step. We compare these two, we see what the difference is, and the difference is called the intercept. And as soon as we get to any of these red letters, they jump down here to that step number 5 to draw on the chart. We write it down here because this is what we want to draw on the chart. So, where are we? Well, let's say we are sailing on the 12th of August. 12th of August. And we have an approximate latitude. That is from dead reckoning. So our approximate latitude is 46 degrees and 14 minutes, let's say. And the approximate longitude is 6 degrees and 48 minutes west, that is north. Where is this? It's on the Bay of Biscay. So on the 12th of August, we're sailing from Spain back to England over the Bay of Biscay, and we'll see what we will be shooting. So here at the time, we've been on deck now, and we've taken the exact time, and the exact time was, in this case, I have to invent something. That was 8 o'clock in the morning, 8:35 minutes and 12 seconds. So this was exact the time that we shot the sun. And when you write this down, you write it on a piece of paper on deck. You start off with noting down the seconds, because they change the fastest, and it's most difficult to remember something that changes fast. Then you write down the minutes, and in the end you write down the hours. It's all in UT, of course. We note the log. So let's say we have sailed 1,234 miles. It's just to make a note what the log says when we do this, in order when we then shoot in the afternoon, again, we will then get a transferred position line. We can also say that we are approximately on a course, well, let's invent something, 285 degrees, and we have a speed over ground of, going quite well, 7.5 knots. So, what did we shoot at 8 o'clock, 35 minutes and 12 seconds? So, on the sextant, we read off 31 degrees and 32 minutes. So, the index error is 4 minutes on the arc. So when it's on the arc, we have to deduct the 4 minutes. So we write a minus here, 4 minutes. And here, when you calculate this, you get a 31 degree and 28 minutes. Now remember this shortcut here, number 2. Tip, simply mark the index error as an extra line on the drum when read off the HO directly. So that means that when you have drawn a second line, you might read off this on the sextant immediately. But for the purpose of using the correction of the index error 4 minutes on the arc, I have here made the example that we have to deduct it. So I haven't mentioned what height of eye we have. So because that's always the same on a boat, let's take my boat. It's 2.8 meters above the water level. So now we need the dip. The dip here, foot number 3, depending on the height of eye, that's what I just mentioned, see yellow page. Remember, yellow page, nautical almanac, yellow page, easy to find. 2.8 meters, that is there. So we'll call it a 3-minute correction there. And that is always negative 3 minutes. So the apparent altitude is now 31 degrees and 25 minutes. Sun correction, number 4, always positive for lower limb, see yellow pages. Well, lower limb, I again forgot to mention, but we always shoot the lower limb, or I do at least. Makes it so much simpler. And we look at the yellow page. We look at the sun, and here the semi-diameter and the parallax and the refraction has all been built in here. So we are in April to September, and we have an apparent altitude of 31.25. So we go down here, 30, what did I say? 31 here. So if you have a look there, so it's between the 29.58 and the 31.33, so it's 14.4 minutes. You have to add those. What did I say? 14.4 minutes. So you have to add these for the lower limb, and you add this, so you get 9 here and 2, 3 there, 31 and 39.4 minutes. So that is what we have as an observed altitude. Now we could do the shortcut again just to check. We had a apparent altitude, or here sextant altitude, of 31, 32 or 28. It's about here somewhere, so you should add 11.5 to that figure. 11.5, so we add this, it's 0.5 in the end, and then instead of 28 it is 39. So you can see how close they are, 39.4, 39.5. So this is, you either decide, either you go the fast way or the slow route, the exact route. If you do it for the RYA, you have to do it the slow route, the exact route. But if you want to do it simple by yourself, well, why not use this little shortcut here? So here we are. So now we have measured the sextant altitude. The next step is, and we don't have any red letters here because otherwise we could drop them down here. The next step is to determine the position of the sun here. So we have to choose a latitude because the calculations only works for full degree of the latitude. So when we have an approximate latitude of 46 degrees 14 minutes, we choose a latitude of the closest full degree. So we could choose between 46 and 47. But since 30 minutes is in the middle of 46 and 47, and this is lower than 30 minutes, 46 degrees would be closer to 46, 14 minutes than 47 degrees. So we'll choose 46. And here on my template, I've already written 00, so you are not tempted to add any minutes there. And we are in the northern hemisphere. Now this is red. So red goes down here, 46 degrees. So we already have the first answer for step 5 to draw in the chart. So how about the declination of the sun? Because that's what we want to see here, the declination of the sun. That has to do with 8 o'clock here. This is the full hour of the declination. We take the full hour, 8 hours, and look at the declination for today. So 12th of August. We'll open 12th of August. Where is 12th of August? Here, close to this, 12th of August. Here we are. So the declination at the full hour at 8 o'clock, sun, 12th, and let's look closer to this. So we have, what did I say? I said 8 hours. 8 hours on the 12th here. Can you see it? We have a declination of 14 degrees and 47 minutes, 47.4, and we shot at 8:35. So that's quite in the middle between 47.4 and 46.7. You see that it's going down every hour. It is going down by 0.7. Can you see that? And you can also see it down here. You have a D factor. The D factor is the difference in the declination for every hour. So if you don't want to subtract them, you can see that every hour it goes down by 0.7. So we have here 8 o'clock, 47.4, in the middle 46.7, so call it 47 minutes. So we have north 14 degrees and 47. 14 degrees and 47 minutes north. That's my declination. So the sun has this latitude, one can say. What's the longitude of the sun? So here we look at, again, the full hour of the Greenwich hour angle. Greenwich hour angle, oh, there's a little 10 there. Let's read what 10 means. At full hour of time of observation. Yeah, that's what I said. So we look here first at full hour at the observation at 8 o'clock. So what's the Greenwich hour angle? So again, we have to look on the 12th of August at the full hour, and that is at 8 o'clock here. It's 298.45.3. At 8 o'clock, 298.45.3. So I'll write this down here. 298.45.3. So what's the increment? Increment, what does that mean? 11. For minutes and seconds at time of observation. See back of almanac. Ah, yes, because this is only for a full hour. Here we did the eyeball navigation somewhere between 8 and 9 o'clock because it only differed 0.7 minutes for each hour. That was the little D factor there, remember? So we can eyeball that. But here it goes so fast because it goes 15 degrees for every hour. So we have to look at the increments for 35 minutes and 12 seconds. And for this sake, we look as it said there in the back of the book. Here are the increments. And for every minute you have one of these tables. So here we have we're looking for the minute 35. This is 35 here. This is all 35 minutes and 12 seconds. So 35 and 12 seconds is here. So I'll show it to you. So where is it? 35 minutes and 12 seconds. So this is the increment for the sun and planet. You see that it says for sun and planets. 8 degrees and 48 minutes. Some other bodies here have some other increments, but we are with sun and planets. 8 degrees and 48. 8 degrees and 48 minutes. So that is the increment. 8 degrees and 48.0 actually. This is the increment for the minutes and the seconds. So we add what it did for 1 hour to what it did in the 35 minutes and 12 seconds. So 3 plus 0 is 3. Now we make a little point. And then 8 plus 5 is 12. No, it's 13 actually. So that's why I have this rubber. That's why I have this rubber. So that's 13. And now comes 4 plus 4 is 8 plus 1 is 9. But you can't write 9 here because there can't be 90 minutes. Because at 60 minutes, it gets to another full hour. So this is, if it says 9 there, it is 1 full degree at 6, and then there are 3 left. So it's 33. Did you get that? That's very important. So you understand that 4 plus 1 makes 9, but you can't write 9 here because it can only be 60 minutes to a full degree. So 90 is 1 degree and 30 minutes here. So let's add here 8 plus 8, 16, 17. We're nice in decimal world now again. 9 plus 1 is 0, and 10, and here we have 3. So we have 307 degrees and 33.3 minutes. That's the Greenwich hour angle. That's where the sun is. Let's read what says number 12. Subtract 360 if the angle is more than 360. Well, that makes sense, because if you add these two, you could theoretically get over 360 degrees. And then, of course, it doesn't make any sense to write 372 degrees or something, because there you deduct then the 360. We only want to have angles between 0 and 360. So now I have this little drawing. It's the Earth seen from above. So this is the North Pole. And here it goes through, you can't see it, but this is Europe, this is America. You can see Greenland maybe. So this is the meridian. So we can now see how far has the sun gone. It starts here 0 degrees, 90, 180. The nice thing with the Greenwich hour angle, it continues counting up behind here on the other side of the world. 180, 190, and so on. So 377 degrees, that's about here, right? So that's where I draw my little sun. And then, where are we? Well, we are somewhere on the longitude 6 degrees. So we are here. So I draw a little boat there, upside down, because that's how we sail. And then it says local hour angle, because that's what we want to have here, is from the boat to the sun. So that's from the boat all the way to the sun. That's the local hour angle that we have. And but we don't know the local hour angle, but we know the Greenwich hour angle of the sun. So that's from here all the way up there. And then you have to deduct our own longitude to get to the local hour angle. So this little drawing makes you, when you are certain, you can just do it very quickly with a shortcut. You read number 13, choose longitude in order to leave local hour angle in full degrees. And then it says subtract for west longitude and add for east longitude. But if you don't really remember this, or you want to understand it, you can do this little drawing, and then you see that you have to subtract here, your own longitude from the Greenwich hour angle. Because your own longitude is this part, and that's what you have to subtract in order to get the local hour angle, which is from boat to sun. So the local hour angle from boat to sun, that should be something which is 0, 0, 0, 0. So that means that we have to choose some smart longitude here. So when you deduct them, it becomes 0, 0. So if you want 0, 0, I think it's a good idea to write 33.3 there. Because if you deduct these two, it becomes 0. That's perfect. So our longitude should have 33.3 minutes in the end. How many degrees? Well, it should be somewhere close to our approximate longitude, shouldn't it? So 6 degrees and 48 minutes. It should be as close as possible to 6 degrees and 48 minutes, but it must be 33.3 minutes behind the degree sign. So you can choose between 5, 6, and 7. That's close to 6. You can try. Well, I would see it's quite obvious in this case. So if you choose 6 degrees, 33.3 minutes, there are not many minutes to come to 6 degrees, 48 minutes. So that is a very good chosen longitude. Because when you deduct these, the local hour angle becomes 0. Let's try. 0, 0, 0. Good. And here from 6 to 7 it's 1. And here it's 0, and that is 3. So now I know that we choose the local hour angle 301 degrees and 0, 0. Why? Because when we go into this book later, this book is about a lot of positions on the Earth. A lot of positions. But only positions with a full degree of latitude and a full degree of local hour angle. So we have to do a little reverse engineering to invent a longitude, because this longitude is not correct anyway, because it's very approximate. So we have to invent a longitude in order to get this local hour angle, which 0, 0 on the back. Again a red one. So our chosen latitude and longitude, the assumed position so to speak, has a latitude of 46 degrees, we have that, and we have a longitude of 6 degrees and 33 minutes west. This is north. So this is the position on the Earth for which we then can see what the pre-calculated altitude and the azimuth is. So that's a very important piece of information. Let's now go into the third book here, or the second book actually, the third step. Now, what we want to do is that we want to find the correct page on in the site reduction table. Now I've left my site reduction table on the boat unfortunately, and I am bound to be ashore right now, so I don't have a site reduction table. This I buy every year, but the site reduction table never changes, so that's why I leave it on the boat. Luckily enough, the site reduction tables are readily available on the internet, and if you don't know where you can find it, I have uploaded them, or I will upload them on my own homepage. Anyway, so I have printed these pages. So what we do now is that, well, I've printed these pages. I've printed 2 pages for this exercise. And this book is really, really thick. So that's why I suggest you not to print the whole book. Buy it by all means at bookharbour.com. You get some 10% discount if you put in the discount code for Reginasailing. And when you buy that, then you have it in a nice book because it has many, many, many pages. But if you just want to get 1 page, you can print it off from the internet. So that's what I've done. So what do? You open that book, and that book is called HO249, fancy word, for site reduction for air navigation. You find the page with your working latitude. What's your working latitude? You have the orange arrow here. There, 46 degrees. So that's what I've printed out here. So see, these are my 2 pages here for 46 latitude and 46 latitude. 2 pages valid for the 46 latitude. And then you look for same or contrary. So same or contrary means, are you and the sun on the same hemisphere, or are you on the contrary hemisphere? So where does this information come from? It comes from here. So you compare this north with this north. The declination is north and my latitude is north. So this is the same latitude. So that's why you find this page, 46, and you look for same. Then, as a third step, you look at the declination range. Do you want to look at the pages from 0 to 14 degrees or the declinations from 15 to 29 degrees? Well, what's the declination of today? Well, it's 14 degrees and 47. Okay, so let's look at 14. So that's why I have this here. So this is for the declination range 0 to 14. And it goes from 0 until the declination 14. How about the 47? They don't have these 47. They only have them by the full degree. That is true. And that's why we have to take this 47 into consideration later here in that box there. But right now, we assume that the sun has a full declination, or the declination of a full degree of 14 degrees. It doesn't, so it has the 47. So we'll look at that later. Good. So now let's look up. Here, look up, it says. The column of the degree, well, you can see here 14. So I have that here, 14. And then we want to have the row of the local hour angle. Remember I said this book is only made for full degrees of local hour angles. Its local hour angle is 301. So let's find this here. We go here, 301 here. I'll show it to you. Can you see that? There it says 301. And here you have three figures. These are the three figures we want to be looking at. What are these? Well, they are the HC, the D, and the Z. All right, well, HC I recognize because that's the calculated angle. But what is the D and the Z? Come that very shortly. So here we can see that it is these figures. So back to our page. HC, that is 31 degrees and 25 minutes. That's almost the angle that we should measure the sun with. Well, what did we measure it for? 31, 39. So it's pretty close. Do you see that? So we're quite good. So it makes sense. That's what I mean. So 31 degrees and 25 minutes. This is only valid for a full degree of the declination. Now we have to take this 47 minutes into consideration before we continue doing this. So that's why we have this D factor. This D says here 42, and it's a plus 42. That's not minutes or degrees or anything. It's a value to show how heavy are these 47 minutes. Because since the sun is more north than 14 degrees, more closer to us, we should measure a bigger angle. That's why we have plus here. Because the sun is more north than 14 degrees, because this angle is only valid for 14 degrees. The sun is closer than 14 degrees to us. It's almost 15 actually. So we should measure a bigger angle. But not quite 47 minutes bigger angle, because that would only be true if the sun was due south. And it's not due south. It's in the morning, so it should be somewhere in the east. So how much is this worth? And that is 42 worth. 42, actually 60th if you want to be precise. So that's just to measure how heavy this is worth. And the third figure we take out here is the Z is 103 degrees. Now, we go over to this box because here we will now use these two to find out how much bigger the angle should have been measured because of these 47 minutes. So we go here, and it says correct HC for minute of declination. That's the minutes of declination. So we write down, we copy this HC again, 31 and 25, because now we have to add something. We have to add this plus, and this plus is the same. But we aren't supposed to add 47, only 42/60th of these 47. And since it's a bit difficult to measure that, calculate that in your head, but you could look at table 5. So this table 5 is actually in the sight reduction table in the back, not in the Nautical Almanac. And it makes sense because it never changes. So in the Nautical Almanac you only have things that changes year by year, and in the sight reduction table you have things that don't change. So here we have now the D factor there of 42. That's how heavy the correction should be from 1 to 60, and this is the minutes that we want to correct for. So it's 47 minutes. 47 is down here, and if you believe me, I'll go down here and look at there. It does say 30. No, I can't see it because I drew on it. 33, that's what I thought. From table number 5, we now know that it is 33 minutes we have to add, which means that the 47 minutes are only worth 42/60th. So we add these two. So 5 plus 3 is 8. 3 plus 2 is 5. 31 degrees and 58 minutes. If you found it a bit difficult to follow why you have to add 42/60ths of these, then you can just do like 99% of all people I know who use the Sextant. They don't understand this table 5 anyway. So all they know is that they use table 5 and go in between 47 minutes of the declination on one hand and the D factor on the other hand, and then they get a correction and they don't really understand what this correction is for. Hopefully maybe you have got a little bit an understanding for why you do this. Now we compare the calculated angle that we should measure on this position with the one that we really measured. And we can see that we did get an altitude of 31 degrees 39 minutes approximately, whereof you should have calculated a 31 degrees 58 minutes on this position. So we have shot the sun with a lower altitude, a smaller angle compared to what you should. Since we have a smaller angle than the one valid for the assumed position, we are further away. So we can draw a line here around away. So we are further away from the sun compared to this position. Now, how much further away? So we have to compare these two figures. So we put the bigger one of these two, 31 degrees 58 minutes on top, and the smaller one, 31 degrees 39 minutes below. Then we deduct these. So that becomes 9, that is 4, that becomes 1. So, and that's 0. So 19 minutes on the arc, 19 minutes on the sextant, these two angles differ. And 19 minutes on the arc corresponds to 19 nautical miles. So the intercept is 19 nautical miles away. So what's the azimuth? That's missing. So the azimuth Zn is a bit similar to Z. It could be Z. Maybe we have to correct it with something. So for you to remember how you correct and what's the Zn, you can look back at the sight reduction table. And up here in the corner, it says what's valid in the northern latitudes, and down here, what's valid in the southern latitudes. So if we zoom this in, or I lift it up, you can see that for the northern latitudes, if the LHA, the local hour angle, is greater than 180 degrees, well then we are ready, because then Z is the same as the azimuth Zn. But if the local hour angle is less than 180 degrees, well then the azimuth Zn is 360 degrees minus Z. And on the southern hemisphere, it's a bit similar. But then we have to do the same with 180 degrees instead, or something similar with 180 degrees, which you can see there. I have also made a little note here. 14 means that this is valid for the northern hemisphere, but in the southern hemisphere you have to do the correction which it says here. So if this is mainly valid for the northern hemisphere, meaning that if your local hour angle is greater than 180 degrees, then we are there. Z then is the same as Z. And if the local hour angle is smaller than 180 degrees, we have to take 360 degrees minus the Z to get to the azimuth. So how do you know what the local hour angle is? Here you have this purple little arrow. You can see 301 degrees. That's greater than 180 degrees. So we are there. So this is the Zn. You can write it down here, 103. Talking with this about the sun, this should not be any trouble at all if you open up your mind a bit and think, because we are in the morning. So where is the sun in the morning? Well, should be some easterly direction, maybe east-southeast, which this is. But if you shot it in the evening, meaning that your boat or the sun would be further away, here you would have a very small local hour angle, because let's play around with this one. So let's say that the sun continues moving around here. So here the sun would be in the evening, which is not now. And the local hour angle is from the boat to the sun, from the boat to the sun. So you can see the local hour angle is very small. So this is very small. It's small, it's less than 180 degrees. So the whole game of all these numbers are very similar, because if you are here and the sun is there, or if you are here and the sun is there, all the angles are the same. It's just that the sun is on the opposite side. It's on the western side of you. So that makes very much sense. So if you get all these right, but your local hour angle is small, meaning afternoon, you should take 360 degrees minus 103. Well, let's just play around with this. It's not valid now. It's just for the afternoon. If it had been exactly the same but in the afternoon. So we deduct this. 3 to 0 is 7, and that's 5. And that is 2. So that means that the azimuth would be 257. And that makes so much sense, because 257 degrees is west-southwest. So the sun would be west-southwest, so the azimuth would be west-southwest. But obviously we are in the morning, so this is not valid. So this is what is valid. So what do we do with this? Now we go to step number 5, draw it in the chart. If you have a chart good enough, with a large enough scale with this position on, well, use it by all means. Otherwise, you have to draw a chart, and I'll come to that in another chapter, how you draw a chart on a template. But if we have a big enough scaled chart, we could write this position into the chart. So let's say this is 46 degrees north. This is my chart, 46 degrees north. And then we have our longitude, which is 6 degrees and 33 minutes west. This is our position. This is our assumed position, or working position, you can call it also. So what is valid from here? From here, you have an azimuth of 103 degrees, because it's in the morning. So that means here is 103 degrees. Well, it's not really, but you know what I mean. Approximately that direction. This is where the sun is. So this is the azimuth. That's the direction of the sun. Approximately. And then you have an intercept. You are further away. So not there. You are not closer. You're away from the sun. So you're along that line. Along that line. 19 minutes. So what you do is you take 19 minutes away from that assumed position, and this is not your position. That's where you draw your position line. 90 degrees to the azimuth. This is your position line, 90 degrees there. And sometimes you draw some arrows in that direction showing this is where the sun is. So we are somewhere along that line. Of course, you don't draw it into that chart. You draw it. Was just a schematic sketch of what you do in the real chart. And we will come back to that, how you draw this in a on a so-called, what they're called? They are called ocean plotting sheets. So southern hemisphere, or ocean plotting sheets on a northern hemisphere. So if you don't have a chart, make your own. But we'll come to that in another chapter. So this is the first example of a sight reduction, and I'll make another one for you if you are still interested.